Okay, hello everybody. Thank you for tuning in. Today I will be presenting Flash Attention 1+2, written by Doan. As this is a somewhat very technical and low-level programming paper, I will not be covering most of those fine-tuned details, but I'll be covering more of the high-level concepts that led to its creation and maybe be able to give some inspiration for similar kind of papers. So. The summary. So TLDR, Flash Attention provides 4x faster, technically even sometimes 8x faster, exact attention. And this means that Flash Attention is not a approximation method for attention or a low rank approximation or any of those methods. It computes the exact same thing as normal vanilla attention. It drops the memory requirements from attention from O of n squared to O of n being sequence length. And it significantly decreases training and inference costs for large models, because if you have faster attention, your GPUs will be used much more often, and therefore reducing the cost of training and inference. Another benefit it gives is it enables large context sizes with no hardware upgrades. An example of this is if you've been using GPT or Claude or any of these large language models in the past couple of months, you'll be seeing that a ton of them have been upgraded to 32K context, 64K context, even Google with 128K context. The reason why that's even possible in the first place is because the memory costs of attention have been dropped from O of n squared to O of n, where plain PyTorch would have out of memory, Flash Attention lets you train much bigger transformers. The first point that Flash Attention kind of brings to attention is time of complexity isn't necessarily about time. There are attention improvements to attention that drop the time complexity and memory complexity of attention down to linear time complexity, but these do not exhibit a similar reduction order of magnitude in actual wall clock inference or training time. Despite this, Flash Attention has the exact same time complexity as vanilla attention. It is somehow also 4x faster. And the reason for that is making use of the hardware. So the subtitle for Flash Attention is exact attention with I/O awareness. And the I/O here is referring to memory. Flash Attention does the exact same computation as vanilla attention, but the caveat is in computing, there are technically two things. There is the actual computation, and then there's also the moving of memory around. If you say wanted to do A times B plus C, you have to first fetch A, fetch B, do the multiplication, move them back, and then do the same with the plus C at the end. And time complexity, as it is usually understood, usually applies to things that look like CPUs, things that look like serial operations. And I'm borrowing this from Jim Keller, which is the beautiful man right there. He's the architect behind the Zen architecture for the AMD line of CPUs. He's a pretty well-renowned person within the hardware industry. And he has one of the most accurate descriptions of computation that I've heard. So there's kind of three different kinds of computation. The first model is CPU. CPUs do things very serially. This is basically what you learn in a traditional computer science degree. It does sequential logic. CPUs can do things like compare and branch, and these are unique to CPUs. So an if clause, like threading as it is understood on a CPU, like branching, prediction like that. And the way you make a CPU faster usually looks like expanding those capabilities, which is why CPUs have these gigantic reorder buffers where you do operations out of order and then you reorder them afterwards. This lets you do things, predict the future, essentially. For example, in older generation CPUs, you would do something like in a for loop to pre-execute a ton of instructions and then reverse course if you turn out to be wrong. And they also have things like speculative execution, which is related to what I just said. GPUs are not like this. So GPUs are designed more so as throughput machines. They do a lot of things in parallel. They can do branching. They're really bad at it though, which is why you don't really do traditional computing on a GPU. And the side effect of not having branching is they're instead strong at doing dynamic memory allocation. They can do stuff like X dereference Y. They can do stuff like fetching memory based on the contents of the computation. So they are very good for the kinds of algorithms that we usually see for neural networks. However, they are not the end game. You can actually go even further, with a third kind, which are DSP paradigm. DSP or digital signal processing unit processors. Some of these aren't even Turing complete because you don't actually need Turing completeness for a lot of these algorithms, like a matmul. You don't need Turing completeness. You also don't need Turing completeness for attention. You actually don't need Turing completeness for the entire transformer. And because of this, some people, particularly Google was the first one who came up with this, designed a TPU. TPUs are still Turing complete, but they are much closer to this paradigm of just gigantic atmol machines that just do things in parallel. They just push, 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 push. They don't do any branching whatsoever because in a transformer or in a training job, you know everything beforehand. You know things statically at compile time, so you don't have to do any of the branching stuff that CPUs usually do. More recently, you see this chip called the Grok chip, Grok with a Q, not a K. This is an incredibly expensive incredibly expensive inference machine. It is an FPGA. It is fully programmable and it is designed from the ground up to do this kind of atmol, just gigantic matmul machines that I have been mentioning. It gives you like 15x sometimes better inference speeds on models like Llama 70B. It's the fastest way to do inference for large language models at the moment. Okay, with that slight hardware introduction out of the way, let's go a bit into how programming works on GPUs. Particularly, Flash Attention focuses on the CUDA programming model, and it is quite different from how it works on a CPU. So on GPU, we have these things called kernels. Kernel is a word that is used for like 10 different things in computer science and mathematics, but in GPU program, it just is a fancy word for program. So when you hear GPU kernel, just hear GPU program. A kernel is comprised of a grid or a ton of grids. Each grid, it contains a ton of blocks, and blocks contain threads. This hierarchy of execution allows you to partition your computation and also partition your memory accesses. A common example would be a general matrix multiply. That algorithm makes full use, not full, it's like 93% use of the hardware by partitioning a matmul into multiple blocks and then does everything in parallel and then recombines them afterwards. Which is why for modern deep learning, people don't actually use the lower time complexity matmul algorithms like Strassons. Almost no one uses Strassons anymore. People use the full O(n) cubed matmul algorithm for all of deep learning. It does the exact computation as just the naive triply nested for loop matmul. Before we move forward, any questions? Feel free to interrupt me because this is quite a bit of content. Okay, so the inspiration behind Flash Attention was the observation that attention is not a compute-bound algorithm. If you look at the picture on the right, that shows the progression of computation growth versus memory speed. And the yellow line shows the compute speed in terms of flops per second, and the second line shows you the memory bandwidth in terms of gigabytes per second. And around the V100, these two lines crossed, and GPUs got significantly faster at doing computation than they are at moving memory around. This means that moving memory around has become a significant bottleneck in most algorithms. So most of the time, your hardware is just hanging, and it's not actually doing any computation. The core is not being used at all. Most of that power and energy is just being used to move stuff around. And related to this is making full use of this thing called SRAM. GPUs, people know about normal RAM, CPU RAM. This is the RAM sticks that you insert to your computer. If you have a laptop, these are probably replaceable for you if you have a not Mac computer. If you have a PC, you probably know these RAM sticks. Most people who've touched a GPU also know about the GPU memory. This is called high bandwidth memory. This is the number you see when attached to a GPU. So if you hear about the A100, usually it's attached with like a dash 40 gigs. The 40 gigs is the high bandwidth memory. And if you look, the high bandwidth memory is an order of magnitude faster than the DRAM. It is super, super fast, which is why it is so expensive. And most people kind of stop here. There is in fact another layer of RAM called SRAM. This is nested deep within the GPU, and it is smaller by an order of magnitude, but is faster by an order of magnitude. So you see, it is 19 terabytes per second memory bandwidth as compared to 1.5 terabytes per second. Flash attention lives almost exclusively within SRAM. And SRAM is unique in that it is not accessible to you if you use any of the high-level deep learning libraries. So PyTorch will not give you access to SRAM. Only compilers and writing raw CUDA will let you get access to SRAM. And so if you want to make full use of the GPU as you have bought it, you will have to kind of get your hands dirty and write some stuff that kind of looks like assembly. Okay, so plain attention. Attention is, we're not going to look at what it really means. We're just going to look at the computation of it. Attention is defined as softmax QK transpose, where QK are two matrices, normalized by root D sub K, and then softmaxed, and then multiplied by V. It's essentially two matmoles. So one matmole is the Q and the QK transpose, and the other one is the softmax V. So two matmoles and one softmax. We know how to make matmoles extremely fast. The problem is that softmax cannot be so easily parallelized because softmax has some dependencies row-wise, whereas matmoles, you can do everything independently. The reason why attention is really important is that attention is kind of the backbone of the transformer. Attention is used in every single attention block within a transformer, and transformers are just kind of taking over the world right now. So if you can find out a way to make attention significantly faster, you have made the entire field of deep learning significantly faster in general. Okay, so let's look at vanilla attention. This was attention as it was used in PyTorch pre-2018, pre-flash attention. You write out that exact algorithm. You write compute QK transpose, you do softmax, and then you do times V. And that's essentially what happens, except if you write it in PyTorch, the memory allocations are pretty terrible. So what you do is not everything happens in SRAM, or not everything happens at once. PyTorch is a complete kernel per operation. So if you do a full round of memory movement between high bandwidth memory and SRAM, so if you wanted to do QK transpose, that's move Q and K from high bandwidth to SRAM, do the computation, move it back. Now, if you want to do softmax, you're going to do that again. So move the result of QK transpose into SRAM, do softmax, move it back. Then, if you want to do the softmax times V, you have to move the softmax matrix and V from HBM to SRAM, do it there, and then move it back. We previously noted that memory movement was the primary bottleneck inside of most modern GPUs. So all of this movement is costing you a lot of time. And the factor of that is about 4x to 8x. So how can we improve it? Well, TreeDAO did it like this. The picture on the right is the high-level diagram of what's going on. And it essentially boils down to two tricks. You can tile QK transpose using the same trick as a general matrix, general matmole. you can basically partition the matmul in such a way that you can do all the computations in parallel. So you never have to load the full Q or the full K matrix into memory at any given time. And the second trick is factorizing softmax. And doing both of these tricks avoids you having to manifest the full QK transpose matrix. That is the primary reason why attention is O of n squared in memory complexity, because Q has a dimensionality of n times d, n is sequence length, d is a hyperparameter, k is the same. So if you do QK transpose, the resulting matrix will be n squared size. And that's the major memory block inside of the attention algorithm. If you didn't have to do that, the entire thing would just be an O of n. Yeah, this is the algorithm in a bit more detail. This is quite a bit, but it's not too complicated. The exact details of it probably would require like a couple hours to discuss, but it boils down to the following. Don't move everything from HBM to SRAM in every computation, and cover everything within a single kernel. If you turn everything into a single kernel, you don't have to do all of those round trips, which is why flash attention first partitions the matrices based on the block size and the size of your matrices, and this is determined by the size of your SRAM. This is a number that most people don't know about, but it is actually a reason why the 3090 card is a significantly worse card than the 4090, despite both of them having the same amount of HBM. The compute-wise, those two cards aren't too different, but the 4090 actually has 10 times more SRAM than the 3090 does, which is why it's so much faster. It's faster, nearly 2x compared to the 3090, despite the flops not being faster. And the reason is all these algorithms aren't bound by the number of flops. They're bound by the amount of SRAM. So you first partition QKV, and then you move only blocks of it into SRAM. And then you have these two nested for loops. One thing to note that is that for loops in CUDA programming are different from for loops in traditional programming. When you see a for loop in traditional programming, you're thinking about doing things repeatedly. For loops in parallel programming actually means partitioning. So if you see a for loop, it actually means divide this job across different cores. And when you see a doubly nested for loop, that doesn't actually mean your algorithm is O of n squared. It technically is, but the way it is executed is the job is partitioned into O of n squared cores and then done in a single step. This is why it's kind of weird, as you'll see later with the way that flash attention scales on GPUs. The algorithm doesn't scale with sequence length at all. It more so just scales with the amount of SRAM you have in terms of time, in terms of actual wall clock time. Yeah, I'm not going to go too deep into the first flash attention because the second flash attention will be just a better algorithm in general. Brief results. So if you look at these two figures, you can see that flash attention gives you a speed up of 2.4x compared to the first original transformer implementation. This is almost faster than all of the other attention improvements like former, linear attention, performer, local attention, reformer, whatever. And the special thing is that all of those guys are doing approximations. All of those guys are not giving you the exact same result as the traditional transformer. They're doing low rank, or they're doing some weird trick to get it down to O of n complexity. And that's the special thing. That, like, despite the fact that flash attention has the same time complexity and does the exact same computation, it can be 2.8 times faster at training at training the transformer. If you look at specific model training jobs, they've trained GPT-2. So they train the small and the medium variant, and it gives them a speed up of 3.5x to 3x. So that's on training, not just inference. Okay, Flash attention 2. Flash attention 2 is almost the same algorithm, except it has one extra new softmax factorization trick and some shuffled memory accesses. That is the essential diagram of flash attention 2. You do almost the same thing as the first flash attention, except we'll get back to it in a bit, but you divide the Q and K matrix very slightly differently. Okay, so before we get into the specifics, we actually have to look a bit into the hierarchy of execution in CUDA programming a little bit again. A kernel is comprised of a grid. Grids is comprised of blocks, and blocks contain threads, but these threads are actually wrapped around warps. Warps are 32 threads collected together. And all of these threads have a shared memory access. So within a single warp, you don't have to do 32 different memory accesses. It's a single memory access and it's shared across the 32 threads. And the technical term for this is that the 32 threads are done in lockstep. This means that they're treated as the exact same computation, which is why, for example, think about a 16 by 16 map. Head math would tell you that this is an algorithm that takes O of n cubed, except on a GPU, it actually doesn't. It is exactly O of 1. Everything is done in a single step. So one memory movement of the two matrices, and then one step, you're done. Okay, so in terms of the improvements, there is one significant change between flash attention 1 and 2, which is how you divide, actually making use of the warps. The first one didn't really pay attention to it at all. The second one actually does. And what they've done is they've shifted the warp scheduling from dividing on the Q matrix to dividing on K and B. This reduction it reduces the amount of reads and writes that you have to do, because Q is essentially used across all of the warps, whereas K and V are only used in subsections of the computation. If you divide on the guy that is accessed a lot, you are doing, by definition, a lot of redundant read and writes. Doing this gives them a pretty significant increase in throughput. And the second trick they've done is refactorizing softmax. It's a lot, except it's just shuffling around the computation in such a way that you can divide softmax into independently computable results. The specifics aren't too important. It's just that by doing this, they can move a lot of these steps from the inner for loop to the outer for loop. And you'll see that in this slide. Yeah, so if you look after the first N4, they're doing those 4 extra lines are the new softmax factorization tricks. So they've reduced the strength of the inner for loop and moved it to the outer for loop.
They get 2 publications out of this?
They did.
That's awesome.
Yeah. It was first in 2018 and this one is in 2020.
Okay.
Yeah.
2 years for.
Yeah. Okay, results. Yeah. It has very significant increases in your speed when doing attention forward and backward passes. They benchmark on an A100. If you look at the blue line, that is naively implementing it in PyTorch. Extremely slow, even compared to plain flash attention 1. Yeah, flash attention 1 is faster, anywhere between 1.5 to like 2x faster to 3x faster. Flash attention 2 is even faster than that. And the very incredible thing to note is at 16K context, PyTorch out of memories. So this class of model is untrainable on traditional like naive PyTorch implementation. You need something like a flash attention that reduces the memory complexity of attention from O of n squared down to just O of n. And if you also note, the x-axis on this graph shows sequence length. Attention is still a quadratic O of n squared times d algorithm, And yet the actual speed of the algorithm does not seem to drop by that factor. And that's because of the differences in the model of computation between a CPU and a GPU. If this was done on CPU, it would, there would exhibit the exact same drop in speed, but because we're doing GPU, it actually isn't.
Is flash attention 2 still computing the exact attention?
Yes.
Okay, that's
Yeah.
cool.
Yeah. Couple of extra results comparing plain. Okay, happy users. I'm just gonna speed run through all of these. These are the libraries that have flash attention implemented into its core kernels. PyTorch, Hugging Face Transformers, Microsoft's DeepSpeed, NVIDIA's Megatron LM, Mosaic ML, Composer Library, UFO AI, GPT, NeoX, Paddle, Hugging Face Diffusers, Colossal AI, implementation of Stable Diffusion, Unifold, OpenFold, Triton, Xformers, Jax, Metal. Pretty much everyone uses flash attention. I'll get back to that in like one slide. This is a massive pain. Companies that use flash attention: Microsoft, NVIDIA, Mosaic ML, Meta.
So I have a question about this. So if it's implemented in PyTorch now,
Mhm.
does that mean that they've got the tricks on their API that they
Yeah.
do that from?
Yeah, flash attention probably added like measurable dozens of megabytes to your PyTorch installs. Because of the fact that it's implemented in the same level of abstraction as assembly, you have to implement it per architecture. So an A100 needs its own flash attention implementation. A H100 needs its own. Let's not also forget about the fact that you can move between vendors. So flash attention on Metal is a completely different algorithm, because Metal doesn't have the same memory hierarchies as the NVIDIA stack, because Metal has unified memory. So it doesn't have the distinction between DRAM and HBM. They're all the same parts of memory. AMD still also has very limited support, and even cards within the NVIDIA line don't have support for flash attention, like the V100 doesn't support it. And so this is a massive pain. And you need a ton of R&D to support anything besides NVIDIA. And there's also currently no mixed precision support, and there's very limited support for low bit D types. This kind of annoys me a little bit, because the tricks that they use within flash attention are essentially two algebra tricks. Why isn't a compiler handling this? Like, why can't MLR or even PyTorch handle this? But I guess that would be room for future research. Yeah, okay. Any questions? Yeah.
So, go ahead.
Yeah.
Sorry, I have one. How has the emergence of quantum computing influenced notions like this, like attention and I guess the notion of attention itself? Because I couldn't help but note, like, sorry to go to the root of the issue.
Yeah.
But like assembly would be, it seems like it's very limited by by how the binary works. But how would a qubit like essentially work with the if we went to the root of the problem, which is this the ones and zeros from the assembly and how it has to build up? What if we do my question is how is quantum computing and I guess the emergence of useful quantum computers influence this field of research?
I'm not by any means a quantum computing expert. I am an enjoyer of the Scott Aronson blog series. He's a popular quantum computing expert. And one thing that he said that kind of popped out to me is that quantum computing is useful, but not actually until we solve the more fundamental block of the quantum error correction codes. We don't have those just yet, so we can't actually reliably use quantum computers just yet. If you look a bit into like the definitions of quantum supremacy, it's not actually benchmarking on any algorithms that we care about. What it's doing is it's generating like a random quantum circuit and then benchmarking that on a normal supercomputer versus on a quantum computer. I think there's actually a lot of room for using quantum computers to probably improve some things in ML, but for now, I think they need to do a bit more research and make them a bit more reliable before we can actually implement it.
There are quantum ML papers out there, they're mostly theoretical, right? And they, I think, haven't been extremely popular just because of that exact issue, that they're not really practical, and mean, I don't know, like the benefits of quantum computing for machine learning are a little bit up in the air without thinking about like. How we can reformulate ML optimization in a quantum computing way. It's kind of like, it's very like anti. The way that quantum computing is used, where you have the superposition in a whole bunch of different states. Like it doesn't like translate really like optimally into quantum computing design in my opinion. But it can, it just needs some work, I
Yeah.
think.
Yeah, there might be a paper in the future that's kind of like AlexNet. Where people design a different way to run ML algorithms on a different hardware architecture, and you might get a thing there, but it's like. No one really knows until people actually do it, so.
Yeah, there are papers though that claim to have like quantum deep learning and all this stuff, but it's, I think, I don't know, they're
Or all, yeah,
sort of minimal impact until they've been actually applied.
yeah, prove it, yeah, okay.
I had a very different question, so, but kind of related to what you said about, you know, towards the end of the presentation, about like mixed precision and having to like create all these bespoke solutions. It is surprising to me that, you know, there isn't like an abstraction for exactly what they did
Yeah.
here, where they like took a matrix multiplication or a succession of matrix multiplications, and then the application of a function, and somehow like broke that up, you know, in terms of the computation graph, and somehow, I don't know, like designed an algorithm that, you know, knowing the computation graph could optimally allocate things into SRAM and other parts of memory. You know,
Yeah.
again, it would be a bespoke solution per chip, but it would work for more general architectures than just the transformer
Mhm.
architecture. And I don't know, maybe it's a harder problem to address.
Yeah, that's kind
certainly.
of the promise of XLA, right? Like XLA is supposed to be doing extremely fast compilation of high level code into things that actually make full use of the knowledge we have in linear algebra. There is a flash attention implementation that is using XLA, but it pales in comparison compared to the tree DAO's like CUDA implementation. But it's not that hard of a trick. It's like two tricks. Like
Right.
yeah, like a just-in-time compiler should be able to during runtime notice that, oh, we're making only partial memory accesses, this and this and this and this and this. Why not just group those together? But who knows?
Yeah, I think the people who like, you know, when they claim to be better, you know, in speed than the factorization based approaches and heuristics, I mean, like obviously they are, because they're, you know, doing a hardware based solution.
Yeah,
Those people doing heuristics are just going to say, well, we can create our own hardware based solution that will still be faster because we're doing a heuristic, right?
yeah.
It's, you know, it's kind of a, you know, there's two kind of branches that people are going down. And I think like a more general purpose, you know, solution for these kinds of tricks would be hugely impactful, but it's probably really hard to do.
Yeah. This paper inspired like quite a few people. I think I read on the blog for the Grok people, Grok with a Q, not a K, that they were inspired by ideas within this paper, because so much of the modern deep learning infrastructure doesn't really need all of that compute or compute capability. Like Turing completeness is one of them. We don't actually need that for a lot of our algorithms, so why not use why even use it? And Turing completeness brings with it a ton of actual problems. Like halting problem is a real problem. It's not like a theoretical problem. It's more fundamental, something like you can't know the future. So you actually have to do the speculative execution. You have to do the reorder buffers and everything. But if you know everything beforehand, if you know everything at compile time, you don't need Turing completeness. You can just ideally allocate everything beforehand and then just push it through. Yeah, some organizations I've been following also make use of this pretty at a lower level, like TinyGrad makes use of these ideas a lot more deeply. Because TinyGrad is trying to break all of deep learning down to a couple of 20 hops, and then having an algorithm, having a compiler on top that cares about how to allocate this within the hardware itself, without just naively compiling it into a handwritten kernel like in Python.
Yeah, that I think is huge.
Yeah.
That kind of solution would work. You know, you run into issues with you know, how they're generalizing deep or reducing deep learning, but you know, people will always complain complain about that, but I think that that's the kind of solution I'm more interested in.
Yeah. Yeah, more general solutions and
Yeah.
yeah, like as much as I like this paper, it's really annoying. Like I tried making my own implementation, it's really annoying. Like the backward pass, like there's a reason why I didn't really discuss it too much. It's a significantly more simple algorithm, but there's like 10 things that can go wrong when you implement it by hand. Just because of how finicky programming in CUDA really is. Like you mess up like an off by one error in normal programming. Gives you a slightly different result. An off by one on CUDA might just might just crash our kernel or something like that, crash our entire program. Yeah, the tool chain is just terrible. It's a swamp. Yeah, Jim Keller said the same thing about CUDA. It's like it's a swamp. It's terrible. It's where all the good ideas and performance improvements are in, but it's not really a place where you actually want to work long term. This is not the end game.
I mean, yeah, it's not so low grade as working in assembly, but it's, you know, it's working in C essentially, and it has all the same problems. So,
Yeah.
Yeah. Working at that low level, that's why people work in higher level abstractions.
I think there's high value in terms of like the papers you can publish if you're willing to code at that level though, because there's so few people that are willing to do it. Like the NVIDIA guy, like the CEO is like find problems that are like super hard to do because then nobody does them.
Yeah.
It's like the more pain you can add to your paper, the less likely somebody's gonna scoop you on it. So.
Yeah, don't always go for low hanging fruit.
Yeah.
I mean, it works though. This paper has a sizable chunk of citations, and he's the sole author, despite having its own lab. Yeah.
So I have a question, please.
Yeah.
Yeah. So the average overall here speed up will be like 2.5 compared to the.
Yeah, 2.5.
Yeah.
It's 2.5 for normal flash attention and 40% above that, so probably 4x for flash attention too.
Great. So it looks like also there is maybe for the limitations. Can we consider also that the SRAM itself, the size of SRAM can be considered here as another limitation that we need to find a threshold value when we see this like overhead of computational in partitioning the Q or K or V and then resampling them again. This overhead looks like there will be a lot of swaps between the HBM and the SRAM in this case. So I have a feeling that maybe the SRAM here, if it is very small, maybe we cannot get this benefit, I mean.
Yes, yeah, the actual bottleneck for flash attention is the SRAM size, which is why I think it doesn't support the B100. Only cards from the Ampere generation onwards, so 3090s, no, the 20 series, so 2080, 3090s, 4090s, so on and so forth, actually support this algorithm. And it achieves a speed up of like 3x, 4x between 3090s and 4090s, despite the cards having pretty comparable flops. Yeah. If you roll back to this slide, the strength of the two for loops are directly linked to the size of your SRAM.
Okay.
Yeah. I mean the intensity of them, yeah.
Yeah, this is actually sounds like a very good idea that they are trying to making. I get like an impression in the beginning that the partitioning itself may a little bit affect the accuracy of the attention itself, but maybe this is actually not right. Maybe actually the only thing here actually is the limitation in the hardware that we trying to speed up with this actual utilization of the SRAM. So I don't think I may be not 100% sure, but I guess the attention accuracy itself will not be affected in this case, even with this partitioning. I mean,
it's an exact solution.
It's an exact algebraic, but I've actually seen from Google that said this is not completely computationally equivalent Because the
Yeah.
partitioning makes it so that you're now doing far more floating point operations compared to the original
That's
one.
true.
Yeah, that is true. You do actually get some numerical inaccuracies just because you're working with floating point numbers. Yeah, this does more computation. It's like time complexity is exactly the same, but it does more computation of floating point numbers, and every single one of those you do, you're multiplying your error rate. So there is a risk of this diverging out, maybe with lower precision floating point number types, yeah. But for 32-bit, it's not really noticeable.
Yeah, this is great actually.
Multiplication is pretty stable though.
Yeah.
So is computing, like, I don't know about the softmax, I mean, it's just a function, right? It should be pretty stable with
Yeah.
operation as well, so it won't be huge.
Yeah, it's not huge, yeah.
Yeah, maybe for something like less stable, like computing power iterations or some like weird linear algebra tricks or other stuff, it might become an issue, but
Mhm.
I don't know, I think.
And did you say PyTorch is using the flash attention too now?
Yep.
Oh,
It's using flash attention too.
so does it implicitly do this or you have to invoke it somehow?
It's implicit, yeah,
Oh.
if you call the normal attention kernel. Yeah, I'm not sure about PrimTorch if it has it, but yeah, normal PyTorch will have it. Probably like 10 megs out of the 500 megs PyTorch downloads onto your computer every time you do install Torch is flash attention. Because it's one kernel per D type, per architecture, or per hardware architecture, yeah.
Well, shows you the benefit of using NN.attention. You have no reason to.
Yeah.
Not to.
I enjoy this talk, and like, coming from a computer science background, like a lot of people in neuroimaging is probably afraid of low level talks, but I think it's good that you're.
Yeah, that's just why I didn't really cover the nitty gritty of how to do this in full CUDA. It's more so just the high level concepts of where to find some inspiration for maybe future research ideas.
Yeah, I mean, like 2 of like the 7 papers that I'm reviewing, they're like, they had to do some compilation either in CUDA or like almost, but not quite with Numbo, which is like a slightly more Pythonic way to deal with CUDA, but anyway. So like if you can, and like in the topology papers that I've read that like either implement like, they like do a filtration, like using GUI or something like this, like a lot of them have to implement like some CUDA kernels or something like this to kind of make the
Yeah,
process faster.
yeah, and you don't actually have to write this always in CUDA. There's a ton of wrappers on CUDA, like Triton is pretty high level. Like Triton looks exactly like Python, it just runs on the GPU instead. Yeah.
What are the limitations with Triton then? Because that sounds like a nice solution.
I think the PyTorch implementation is written in Triton.
Oh.
The limitations of Triton are Triton is a work in progress piece of software. I ran into Triton bugs while doing Triton tutorials before. So it's not the most stable piece of software in the world, whereas CUDA is basically rock solid. Yeah, yeah.
Yeah, and there's a lot of interesting algorithms that you can apply to stuff that I'm interested in, but like this, like because I've spent most of my life working with CPU algorithms, like the algorithms I think are all CPU algorithms, and then like you're like, okay, like I want really nice and robust data structures, but I'm like, wait, CUDA doesn't have really nice and robust data structures.
yeah.
It's like like I need a tree. What give me a tree? And they're like, so you can't like you have to like block your algorithm up into like little cubic partitions in order to kind of replicate the type of parallelism that you could probably imagine with a tree.
Yeah, modern computers are really weird. I don't think like most computer science programs these days can actually prepare you for how weird they are. Like if you think about like hash maps, you think hash maps are always faster than most data structures. They're actually not, due to how memory accesses actually work, even on a CPU. You can have sequential memory accesses are sometimes even faster than using hashing functions because of cache hierarchies and everything. Yeah, it's really weird.
And it's you did school at GSU, right? Did they have a CUDA course?
They did not,
They
yeah.
Yeah, I had to do one in a tutorial when I did undergrad.
Uh-huh.
It was very haphazardly put together.
Yeah.
That was almost like 10 years ago now too, so it's probably.
You took it at Tech?
What was that?
What, you took it at Tech?
No, I went to school in Florida
Okay,
for undergrad.
okay. Any other questions, people online?
Thank you.
Okay. Thank you, everybody, for tuning in.
I don't know.